Yeah, thank you. So, thank you for your invitation. And oh, what happens? Sorry, so something happens.
We can still see your screen.
Yeah, so I have a problem.
Oh, okay.
This is the problem. Okay. Okay, so sorry, let's start. Thank you for your invitation. So today, I would like to tell you our latest progress of the neutron star merger simulation. So first of all, I'm sorry that some of the my talk may overlap with talk last year, but perhaps readers, audience are different, and then so I think that's okay. So anyway, so this is the content of my talk. So after the brief introduction, I would like to show you our latest progress in the neutron star merger simulation. So first, I would like to talk about the neutron star merger simulation and the post-merger simulation separately. And then our latest simulation, our latest second long simulation for black hole neutron star merger. And then I will summarize finally. Okay, so this is perhaps I don't need this introduction, but I would like to remind you that the fact why neutron star merger is interesting. So neutron star mergers are predicted to be a source of the short gamma ray burst. And also neutron star merger is predicted to be a promising site for the R process nuclear synthesis. And also it's a kilonova, a source for kilonova and macronovas. And also it's a very important site for studying a nuclear equation of state. So through the latest inspiral gravitational wave form. And what is nice was that in GW17, so every aspect has been shown, and then these predictions are actually by GW17 proven. However, we have only one event, and we don't know what happens for the next event. The reason is that in the last 2 or 3 decades, many numerical relativity simulations have been done, and then we have found that there would be many possibilities for neutron star merger. For example, if a total mass of a neutron star is larger than some threshold mass, after the merger, black hole is soon formed, and then and only for the presence of asymmetry of neutron stars, binary neutron stars, we could have this. By contrast, if total mass of a system is smaller than the threshold mass, initially, at least temporarily, massive neutron star is formed, and then subsequently, through the complicated process by the magnetic hydrodynamics or effectively viscous process, and neutron cooling and so on. So massive neutron star evolve, and the mass is high enough, so then it collapses to eventually black hole and surrounded by this. Also, if total mass is not very large, so massive neutron star or very long, which doesn't collapse the black hole or its lifetime is very long, could be formed. And then naively thinking there are many possibilities, and then electromagnetic counterpart could depend on the fate. So then what is important in numerical relativity community is to explore the wide variety of possibilities. And the other important aspect for the binary neutron star merger is that it's a promising source site for the R process nuclear synthesis. This figure is a well-known figure by Smedin, and this shows that solid curve shows the R process abundance, so solar R process abundance pattern, and point shows the abundance pattern from the observation of the metal poor stars. And anyway, so this figure shows that the abundance pattern is quite similar. So this is a so-called universality. So universality means that so this suggests that the source for R process, so main source, dominant source for R process nuclear synthesis is likely to be one same event. then neutron star merger is predicted to be such a predicted to be the promising site for such a process nucleosynthesis. However, again, there are many possibilities for the merger of binary neutron stars, and then naively thinking, there should exist a variety of nucleosynthesis abundance pattern, and then one important task is just to explore what happens for each phase. To the nucleosynthesis abundance patterns. So this is another important topic for numerical relativity. And then to summarize interaction, role of numerical relativity is as follows. First, we should perform a numerical relativity simulation for a wide variety of parameter space. Parameter space means that mass and the equation of state, and provide information to the predicted signals, like electromagnetic signals, gravitational waves, cosmic ray, and neutrino, and so on. And the second important role is to explore the R process nucleosynthesis. Specifically, one important question is that whether the universalities can be reproduced or not for every possible fate. And also another important question from the observational side is that what observable lines for heavy element. So as Kent talked yesterday. And also numerical relativity simulation is play an important role. So in preparing a setup for the post merger for the post process simulation, like jet simulation for gamma ray burst, and also for the nucleosynthesis and so on and so on. Anyway, from this aspect, numerical relativity simulation is important. Then what should be done in numerical relativity? This shows the timeline for the neutron star merger. So after the merger occurs, and then dynamic mass ejection occurs. This is induced by shock heating and the tidal effect. And it proceeds in a very short, for a very short time scale, so typically about 10 milliseconds. After that, typically, as I already showed, remnant is a compact object. Compact object means that black hole or massive neutron star surrounded by disk. And from such disk, through the MHD or viscous effect, post-merger mass ejection occurs. And the key ingredient in the post-merger mass ejection is angular momentum transport, and angular momentum transport is determined by so we believe that it is determined by the MHD effect. And also observation shows that observation shows that short gamma ray burst continue for about 2 seconds, and so we believe that binary neutron star, at least some of binary neutron star merger is a source for short gamma ray burst, and then within about a few seconds, gamma ray bursts are likely to be provided. And this is in a sense interesting history for numerical relativity. And in addition, another very important aspect element ingredient for binary neutron star merger is nucleosynthesis, as I said. And then to explore the nucleosynthesis, we have to take into account weak interaction because it plays a very important role. Specifically, in simulations, electron fraction is a key quantity for determining the R process nucleosynthesis, and we have to be careful in analyzing electron fraction. Anyway, these are stuffs to be explored in numerical relativity and associated post-process simulations. And then to summarize, we have three important time scales. One is the dynamical mass ejection time scale. It's quite short. And second is the post-merger mass ejection time scale. It's quite long, so about 1 second, and the short gamma ray burst time scale is typically 1 to 2 seconds. And then the role of a numerical relativity is to investigate the phenomena with these three time scales. So that means that, anyway, so constraint comes from the longest time scale, and then we need to evolve the post-merger system at least several seconds, hopefully 10 or 20 seconds. And in addition, so input physics is very important, as I said. MHD effect and so effective viscous effects are key to post-merger mass ejection. And perhaps MHD instability play a role for inducing short gamma ray burst. So then anyway, so this is one of the very important physical input. And as I already said that also for exploring the nucleosynthesis, we have to take into account very carefully, take into account weak processes. Weak process means that not only neutrino emission, but also for a wide variety of weak interaction like beta decay and so on. So that implies that ultimately, so we need a seconds long GR radiation, neutrino radiation MHD simulation with input of weak interaction and also a realistic equation state for neutron star. Anyway, so this is a milestone goal for numerical rapidity in this field. And then to this goal, so currently there are two approaches. One is that the so-called separate approach. The separate approach means that in the first, so we performed just merger simulation only for short time scales. So typically, so less than 100 milliseconds. And then so post-merger simulations are performed for a long time scale, so for 10 seconds or something like this. France already talked about this on Tuesday. And the other more direct and more favorable approach is just perform a simulation for second run. But it's a little bit expensive, but now so it's getting possible. So then, so in the second part, I'll talk about the second approach. And then so nucleosynthesis and kilonumber light curve estimation and GRBZ and so on are analyzed as a post-process. So yeah, it's quite difficult to do everything. So I think that for milestones, so two approaches are possible. Okay, so first, so I would like to talk about separate approach. So actually, we have been working on this for the last 5 years. And I think that now it's getting popular approach. So as already talked by Francois. And I think that this is a solid approach to specifically explore two mass ejection mechanism. And so, and from now, so I'd like to summarize that, so what we have learned from this approach. So I think that, so first, so about dynamical mass ejection. And so for this, many numerical activity simulations have been done since 2013. And in this decade, I think that property of dynamical ejector have been well understood. Of course, so details, quantitative details determined by, for example, the neutrino irradiation and the neutrino transfer are still not very clear, but I think that at least quantitatively, we have obtained a good understanding for this. And what we have learned as follows. First, mass. Mass is between about 0.1% to 1% of solar mass. And many simulations show that for low total mass leading to a massive, long-lived massive neutron star formation, in such case, typical dynamical ejector mass is not very high, so 10⁻³ solar mass. But if hypermassive neutron star is a remnant, in such case, dynamical ejector mass could be 1% of solar mass or something like this. Yeah, I think this is, of course, so yeah, we have error, but I think that it's we have consensus about this. Also, electron fraction is relatively low. So relatively low means that between 0.05 and 0.4. I will show later about this. And so this means that it's a very suitable for producing so R-cross element, R-cross heavy element. And also dynamical ejector mass is fairly fast. So average is about 20% of speed of light. but could be, so it could be up to 90% of the speed of light. So these are what we have learned in the last decade. By contrast to the dynamical ejector, so physics that for determining the post-merger ejector is highly complicated. So the reason is that the remnants are magnetized, and then so magnetic field is for post-merger mass ejection, magnetic field MHD instability play an important role, and that means that we have to understand understand the MHD instability and the role of the magnetic field. And so broadly speaking, there are two important roles by magnetic fields. One is that due to the MHD instabilities, turbulence excited, and then so effective viscosity is enhanced, so very high. And then so due to effective viscosity, angular momentum transport and viscous heating occur, and then so this determines the evolution of the disk and the mass ejection. In addition, so because we could have the global magnetic field due to the MHD instability, due to the dynamo, in a sense, dynamo due to the MRI and the convection. Then, so in such case, purely MHD effect, not the viscous effect, play a role. These two effects determine the efficiency of post-merger mass ejection, and so anyway, so ideally, so performing a MHD simulation is necessary to follow the post-merger mass ejection. And in addition, so for this process, so before saying that, so but so in the last 5 years, we have found that the ejector mass depends on the remnant. For example, if black hole is formed, then so due to the absorbing nature of black hole, so then so mass ejection is suppressed, and the typical mass of typical post-merger ejector mass in the presence of black hole is about 10% of initial disk mass, and that means that about roughly speaking 1% or 2% of solar mass. By contrast, in the presence of neutrons, we don't have an absorbing system, and then so post-merger mass ejection is enhanced, and ejector mass could be the 30% to 50% of initial disk mass, and then so ejector mass could be fairly large, so much, roughly speaking, 5 or 10 times larger than the ejector mass for the black hole formation. And so also recently found that interaction plays an important role. So weak interaction here means that not only neutron reaction, but also the beta decay and electron capture and positron capture and so on and so on. These all play an important role. Then so why so why is so weak interaction important? So this is so this can be understood by showing that how the mass is ejected. So this I'm showing that the basic picture for mass ejection in the post-merger stage. Anyway, so as I said, so in the typical outcome after the merger, so is that black hole neutrons are surrounded by disk, and then so disk is likely to be highly magnetized, and then so due to the magnetic field instabilities, magnetic field is amplified and the viscosity is enhanced. And then so viscous heating occurs. However, so in the early phase, typically disk temperature of disk is fairly high. So high here means that higher than a few MeV. In such case, efficiency for neutrino emission is very high, and that then so even if heat is generated by viscosity, neutrons carry away such heat. And then in such case, so even in the presence of the viscous heating, disk does not expand efficiently. Of course, in the presence of viscosity or MHD effect, angular momentum transport works, and then so disk expand, but this expansion is not efficient enough for mass ejection because of the neutron cooling. However, so due to the viscous angular momentum transport, disk expand like this. And then so due to the adiabatic cooling, so temperature decrease. And then so eventually after temperature decrease below the a few MeV, so viscous heat cooling, Newton cooling become less inefficient. And then so viscous heating is fully used for the disk expansion and mass ejection. So this is a basic picture for the mass ejection from the system, post-merger mass ejection from the disk. And so in this case, so time scale for post-merger mass ejection is determined by this effective viscosity, and effective viscosity is often determined by the alpha parameter, Shackler-Siniak parameter. And if we choose a typical parameter, then so viscous time scale is roughly speaking several hundred seconds to 1 second. So anyway, so it's much longer, about 100 times longer than the dynamical mass ejection time scale. So let me show the one animation. This shows the animation for the viscous evolution for disk with mass 0.1 solar mass, which is surrounding the 3 solar mass black hole with spin 0.8. And in this case, alpha viscous parameter is chosen to be 0.05. Yeah, anyway, so in the initial stage, simply due to the viscous angular momentum, disk expand. So in this case, let's try again. In this case, after about 1 second, so Newton cooling becoming inefficient and mass ejection. Okay, now is a mass ejection phase. So yeah, we performed and many other people performed this kind of simulation, and then so we found that typical mass ejection time scale is several hundred milliseconds to 1 second. This also agree with the result by Francois, which was shown on Tuesday. Then so the next question is that then so what is the typical value of YE, the electron fraction in the post-merger mass ejection? So this is completely determined by the weak interaction. Initially, disk density is very high, and then so yeah, neutrinos are also essentially trapped. And in such case, so this kind of a beta equilibrium is established. And so in this beta equilibrium, each element abundance is determined by the so this chemical equilibrium. So this is a chemical potential. But in this stage, so electron degeneracy is very high, and then and the neutrino chemical potential is essentially 0. So then so this is very high. So then so this should be small, and this is comparable. So then as a result, in the high density state, Y is low. So electron fraction is so proton fraction is low. That means the electron fraction is low. And this continues for a while, but after the viscous expansion, density decreased. And then, so as a result, initially, neutrino absorption is decoupled, but still, so we have this kind of the interaction process. So in this phase, so what is important is the electron capture and the position capture. And these reactions have to be taken into account very carefully. And in this stage, still so ratio of the proton to neutron is determined by weak interaction. But however, so if maximum temperature decrease below about few MeV interaction, this also interaction completely decoupled. And then in such stage, Y is determined because weak interaction become important. So then, so that means that at T max is about 3 MeV. So if we calculate this relation with a given density and temperature, then so electron fraction is determined, and then so people usually found that the typical value of electron fraction is 0.3. So yeah, this is completely determined by the weak interaction together with the angular momentum transport time scale. So, but anyway, so these values are still neutron rich, but it's not very small. So as a result, heavy element production is suppressed. So this is what I think that the latest our understanding. And previously, so some community often emphasize that electron neutron heating play an important role for determining Y, but essentially we found that so this reaction determines the electron fraction. Okay, so then this is in a sense a summary figure for obtained by two approaches. So as I said that so in the first 10 milliseconds dynamical mass ejection occurs, and then this is a histogram of a horizontal axis shows the Y and the vertical axis shows the mass fraction. And so in the first 10 milliseconds, so dynamical mass ejection occurs. Then we have this kind of a broad Y distribution, not only for the neutron star, massive neutron star, long-lived neutron star, massive neutron star case, but also the short-lived hypermassive neutron star formation case. However, so as I said that in the case that long-lived massive neutron star is formed, in such case, so total mass of the system is not very high. In such case, dynamical ejecta mass is relatively low. So then, this is fairly low. By contrast, for the formation of the short-lived hypermassive neutron star, we often have the fairly large mass. This is due to the efficiency of shock heating is high. And subsequently, in the post-merger phase, we have the post-merger mass ejection. And as I said, due to the long-term viscous evolution and Y become large and typically 0.3, and then distribution is shifted to the high Y side like this. And then this mass is also is dependent on the fat is the central object. And in this case, neutron star is a central object. So then we don't have the absorber at the center, black hole. We don't have black hole. Then in such case, mass ejection from disk is enhanced. By contrast, if black hole is formed, so mass ejection is suppressed, and in this case, mass is about 10% of the for this case. So this shows that the ratio of the ratio of the mass of dynamical ejecta to the post-merger ejecta depends sensitively on the fat is produced after the merger. So this is one important aspect from our latest studies. But this is very important for nucleosynthesis. So anyway, this is a summary. So there are at least 4 patterns. So as I said that for the case that the long-lived neutron star is formed, then dynamical ejecta mass is small, but the post-merger ejecta mass is high. But in the presence of the if the hypermassive neutron star with short-lived hypermassive neutron star formed, then we could have the relatively high dynamical ejecta mass, but relatively low dynamical post-merger ejecta mass like this. And in the case of symmetric neutron star merger, efficiency of shock heating is high. In such cases, temperature is enhanced, and then as a result, Y distribution is could be could have a high Y like this. However, in the presence of sufficient asymmetry in binary neutron stars, in such case, shock heating is suppressed. Then higher edge of Y shifted to lower side. And also in this case, because of the asymmetry, disk mass is a little bit higher than asymmetric case. In such case, post-merger mass ejection is enhanced like this. But and also this is a black hole neutron star case. I will show you the result later for this. But anyway, in this case, dynamical ejecta mass has only very small value of Y. But post-merger ejecta mass, post-merger ejecta has a very similar distribution as a binary neutron star case. Anyway, this figure is just summary of what we have found in the last 5 years. And then, this is a result for the nucleosynthesis. As already said that if long-lived massive neutron star is formed, we have a large post-merger ejecta mass, which forms a relatively low R process element, low mass R process element. By contrast, in this case, dynamical eject masses are low, and as a result, heavy R process element is suppressed. So then, curve becomes something like this. I should say that this is not very, of course, precise, but so this tendency doesn't change. So what I would like to point out here is that so this dot shows the solar abundance pattern, but in this case, because of the huge amount of the post-merger ejecta mass, so it's quite difficult to reproduce this abundance pattern. But by contrast, in the presence, if short-lived massive neutron star, hypermassive neutron star is formed, in this case, so post-merger mass ejection is suppressed, and then so we have a very good so blending of a post-merger ejecta and the dynamical ejecta. So anyway, so in this case, well, blending is not very good, but this is a very good blending. But this could be just by chance, and then so we need to explore the fairly larger parameter space. And in this paper, we performed 5 simulations, and then so this is a result for the elemental abundance pattern. And you can see that, well, so irrespective of the parameter space. So for example, for this case, mass, so system is symmetric, and this is highly asymmetric, and in this case, system is a little bit heavier. But irrespective of the choice of parameter, abundance pattern fairly agree with the solar abundance pattern. Yeah, of course, for this case, so some deficit of post-merger mass ejecta, but anyway, so compared with this case, so yeah, agreement is much better. And by contrast, for the case that long-lived massive neutron star is formed, so it's quite difficult to reproduce a solar abundance pattern. This is our latest result. So in the presence of a MHD effect, so I mean that in the presence of a MHD effect, so we have the global magnetic field effect, and then so in such case, so usually people find that high, so find the higher low IE element, but even in the presence of a MHD effect, it's not very easy to reproduce the solar abundance pattern. So then, so we have reached the following prediction. So prediction and the resultant prediction. Only when the remnant of a binary neutron star collapsed to a black hole in a short time scale. So short time scale means that in 10 to 100 milliseconds after the merger, universality for abundance pattern can be reproduced. So then suppose that binary neutron star merger is the main site for the R process nucleosynthesis, then so long-lived massive neutron star formation should be a minority. Otherwise, so from our result, we find that it's quite difficult to reproduce the solar abundance pattern. So this suggests that short gamma ray bursts from a remnant magnet should be rare. And also, this is consistent with the absence of a radial source. So this was a topic of a talk of Kenta yesterday. In other words, in case many long-lived massive neutron star formations are observed in the near future, so then so neutron star merger scenario of R process nucleosynthesis may be excluded. But anyway, so yeah, so what? Exploring the R process nucleosynthesis is also very important, because it could kill many interesting scenario, or yeah, just prove the interesting scenario. Okay, so in the last 10 minutes, I'd like to show you the our latest second long-term simulation for black hole neutron star merger. So here, let me explain why we focus on the black hole neutron star merger. The reason is very simple. So time scale, so time step of the simulation is determined by the current CFL condition multiplied the grid spacing, but for grid spacing is basically determined by the black hole mass. And then, so if we choose a fairly high black hole mass, so this becomes longer, and then so we can continue the simulation relatively longer. So this is a motivation why we perform the black hole neutron star simulation as a first step. And this is our simulation result for density and the magnetic field strength and the ratio of the magnetic field energy density to the rest mass energy, electron fraction, temperature, and entropy per volume. This is a case for black hole mass, about black hole mass of 5.4 solar mass and the dimension of the spin is 0.75 and the neutron star mass is 1.35. Anyway, so after the tidal, so in this case, tidal dispersion occurs, then and the disk is formed. And inside disk, magnetic field is amplified initially by winding and subsequently by MRI. And then after the sufficient amplification, eventually we have a strong magnetic field penetrating a black hole, and then outflow along the rotational axis is enhanced. And due to the amplification of magnetic field, effective viscosity is enhanced, and then disk gradually expand. And then also temperature gradually decrease, and at some point, neutron emissivity become low enough. Then post-merger mass ejection is enhanced. This scenario is essentially same as which I said in the previous slides. And then this entire scenario can be now examined by numerical relativity simulation, at least for black hole neutron merger. Anyway, so this continues until 2 seconds, but I finish here. So this is evolution of the electromagnetic energy and the ratio of the electromagnetic energy to internal energy, ejecta mass, and neutron luminosity. And as I said that initially, after the merger, electromagnetic energy is enhanced initially by winding and subsequently by MRI. Then increases saturated eventually, and then after that, due to the disk expansion, electromagnetic energy decreases time. And at the saturation, ratio of the electromagnetic energy to internal energy become about 0.1 to 0.01 to 0.1. But anyway, equipartition, so saturated ratio is obtained. And this shows the mass ejection history. So initially, due to the tidal disruption, dynamical mass ejection occur. But subsequently, we have a quiescent phase. So during this phase, magnetic field is amplified, but and the neutron luminosity decreases gradually with time, like this. But at some point, then neutron luminosity become small enough, and then post-merger mass ejection is enhanced, like this. So all these scenarios were already found in the separate simulation. So merger simulation and post-merger simulation, but this can be proven by a self-consistent long-term simulation. And this is histogram of the Y histogram. And as I already said that by the dynamical mass ejection, we have a high ejecta mass with a very small Y, and from the post-merger mass ejection, we have the fairly high electron fraction elements like this. And this is also very good for approximately, well, not approximately, well, fair agreement with the solar bands pattern. This is elemental pattern. And this red shows the total elemental pattern. The blue shows the contribution from dynamical ejector. But anyway, so by summing up the post-merger ejector component and the dynamical mass ejection components, then we could have a fairly good agreement. And so this is a final slide, and this is just for enjoying the looking for animation. And this is animation from our latest simulations. Previously, in the first paper, we imposed the equatorial plane symmetry, but in the absence of equatorial plane symmetry, we have something new qualitatively. So this is this shows the left side shows the rest mass density and magnetic field line. So magnetic field line penetrating a black hole, and the right panel shows the magnetic field strength. But then so qualitatively, so the evolution is very similar to the previous slide, but so some new qualitative finding will be found. The initial after the merger tidal dispersion, the disk is formed, and in the disk, magnetic field is amplified, and eventually, strong magnetic field is established near the black hole, and we have a black magnetosphere penetrating black hole, and then so we have the outflow. But in the absence of the equatorial plane symmetry, so outflow is asymmetric naturally. But besides this new finding, and evolution is quite similar due to the magnetic field amplification, so viscous effect play a role, and then disk expand gradually. And in addition, we have the outflow like this. And after the Newton luminosity decrease below a threshold value, so post-merger mass ejection is started. And all these properties are same as before. And for example, in this case, we have only one jet. So this is due to the absence of the equatorial plane symmetry. But if we wait for a couple of 100 milliseconds, so again, we have a outflow in the other direction.
Sorry, you have 3 minutes.
Yeah, this is final. This is final slide, and as I showed, now it's possible to perform a second long simulation, and the next step is to perform a simulation for binary Newton sum mergers. And now so Kenta is working on this. And of course, so there are many ingredients to be improved. Yeah, of course, as many people in this conference talked, and we need a better radiation transfer. It's essentially never ending mission. But also, as I said, that angular momentum transport is very important in the post-merger phase. So, so this is a key for determining the post-merger mass ejection. And for this, MHD effect is a key. And so also resolving the many MHD instability is a key. So for this, so high resolution MHD simulation is necessary. Also, this is a never-ending story. And so the other important topic is how the remnant neutron stars are evolved in the presence of a long-lived massive neutron star. In this case, so perhaps dynamo inside the remnant neutron stars play an important role. But for this, again, so long-term simulation, taking into account magnetic field amplification and the convection and the turbulence and so on is necessary. I think that this has not been done seriously, so maybe it's an interesting topic for the future. Also, this topic is very important. So to explore the final profile of the global magnetic field around the remnant neutron star. Okay, thank you very much. That's all.
Thank you, Masaru, for the very nice talk. I don't see anyone with questions yet, but does anyone have questions for Masaru? Yeah, Zvi, go ahead.
Hi, Masaru. Thanks for this very nice talk. I'm puzzled about this your conclusions about long-lived remnants and short-lived remnants.
Yeah.
In particular, how does it work in the context of 1708-17? Because in 1708-17, how do you classify it? Because there is some evidence, as you know, that for a significant R process above the second peak.
So
in 1708-17. So how is this consistent with your picture here? How will you classify it?
I believe that so for this case, so the remnant should be something like this because of the absence of the long-lived massive, long-lived magnet as well. So I believe that this is not the case. So as is the case, and for this case, so best estimate for mass ratio is fairly different from unity. So then, so I believe that this case, so asymmetric Newton star binary leading to short-lived massive Newton star is likely to be GW70 or 70. But this is what I believe. So I'm not, yeah.
No, I want to hear what you believe. Yeah. Short-lived. So how you define short-lived? 1 second.
1 second. 1 second is too long. So yeah, 100 at the longest a few hundred milliseconds. So 100 milliseconds. And then so after that, so yeah, naively thinking after that, we have a disk and a black hole, and then so in the disk we have a dynamo and amplification, and then so yeah, spending a few or several hundred milliseconds, magnetic field is amplified, and then after that, so we could have gamma ray burst. So this is my naive expectation.
This is a little bit in contrast with this conclusion by Margalit and Metzger that they wanted something like longer lived. I'm not sure what's the time, but they claimed that it must be a little bit longer. But this is very interesting question to put this picture that you had here in the context of 170817 and
yeah. Thank you.
Thank you.
So I see a question by Bayham in the chat. Would you like to ask it, Bayham, or should I just go ahead and read it? I guess I can read it. It says, I'm sorry if you have already mentioned it, but I would like to ask, how would the magnetic field effects? Sorry?
Like to ask how, okay.
Okay.
And the question is that I would like to ask, how would the magnetic field affect the R process nucleus? So this is for post-merger mass ejection, perhaps, and then so yes, so yeah, anyway, so this question can be answered if we perform the self-consistent simulation, something like this. Then, so from this simulation, we found that let's show you the. We found that after the merger, in the disk, magnetic field is amplified, and then so effectively viscous angular momentum transport occurs, and then so mass is ejected eventually after the neutrino luminosity decrease. So this is the basic picture, but in addition, we have a global magnetic field. For example, this is a global magnetic field. So this shows the global magnetic field around the rotational axis. Then under this global magnetic field rotates due to the black hole spin. And then so we have the rotating global magnetic field around this rotational axis. And then in such case, also this play a role for mass ejection. So that means that not only the viscous effect, but also the effect, something like Blandford pain. So magnetocentrifugal effect play an important role. So, but it's not very easy to distinguish one by one. But anyway, so this simulation shows that we have two effects. One is effectively viscous process due to the amplified, the turbulent magnetic field. Also, the other is a global magnetic field. Something like this. Yeah. I hope that I answer your question.
And we now have Antonius with his hand up. So if you want to go ahead and ask.
Hello, Masaru. Thank you for the nice talk.
Yeah.
One question that I had is, it seems that from the plots that you have shown us, and this is again going back to the question that we asked, the simulations regarding the ejecta and all these issues are favoring, as you said, a short-lived remnant. But I remember a paper some years ago regarding the maximum mass of the neutron star, where your group were arguing about a longer-lived supermassive neutron star that essentially collapses on the turning point line. So I wanted to ask how these two results somehow, how you can conciliate these two results, and what is your ideas about that?
No. So what I said 3 years ago is that neutron. So from the observational result at that time, so still 2.3 solar mass is allowed. But so of course we didn't say anything about that. Well, it's not a 2.1 solar mass or 2.0 solar mass or something like this. So that means that it's still consistent. So then so I guess that to get this result, perhaps maximum mass of neutron star is not very high. But yesterday I heard from Mihail Kramer, so then he said that he discovered a very high mass binary neutron star. So but it's not very clear. But anyway, so if so we take into account only this simulation result, so then this is naively consistent. Or as Toby said that we could have some reason why so people usually believe that in the presence of magnet, we could have very strong radio emission, but in some reasons, so radio emission might be suppressed, but I'm not sure. But anyway, so 3 years ago, we wrote a paper, but nothing is inconsistent with this result.
So you still believe that in GW17 or H17, the star collapsed as a supermassive remnant? So I believe that it collapsed the black hole. Here is a very short time scale. Now, Well, anyway, thanks.
Do we have any additional questions? If not, I guess we can take a short 5-minute break.
Hello.
Hello. Yes.
First of all, it is a wonderful talk. I have a question. Actually, I have just completed my master's in physics and I'm still very new to the field. But I would like to ask a question. It is about what do you think about the violent supernova explosion that leaves behind neutron stars and black holes? Is it so powerful that it can destroy the binary system altogether?
Sorry, say again. So your question is about supernovae.
Of course, about its explosion actually. How violent is the supernova explosion that leaves behind neutron stars and black holes? Is it so powerful that it can destroy the binary system altogether?
Maybe so. Please speak more slowly. So I'm not good at hearing English. So please speak more slowly. So.
Okay. I'm asking about the supernovae explosion. So I'm saying,
You're saying that black hole or neutron stars are formed, and then so what was your question?
Pardon?
So what was I couldn't hear your final part.
Actually, I'm asking that is the supernovae explosion is so violent in nature that it can destroy the binary system altogether?
Well, it's up to the condition. Of course, if usually if more than half of the mass is ejected from the binary system, so system could be destroyed. But it's up to the condition here. So it's up to the separation, so orbital separation, and how much mass is ejected and something like this. But typically, so we say that more than half half of the total mass is ejected from the system, so system is destroyed. Yeah, this is a naive estimate.
Okay, thank you so much.
Yeah.
Okay. Are there any additional questions? So if not, we can take a short break and reconvene in 5 minutes for Andrew.